Hello everybody, this is the notes for Calculus, section 3.2. What we are talking about is continuity or continuous functions, continuity sometimes. So, for a function to be continuous, the simple idea, as it says, is if you can draw the entire graph without lifting up your pencil, then it's continuous. Now, that's not a very good definition, but that's the concept of it. The detailed definition of a function that is continuous says a function f is continuous at x equals c if you meet all three of these conditions. So the first one, the function has to be defined. You plug in that x value, you're going to get a y value. Okay. The second requirement that needs to be met, the limit at that x value, it needs to exist, and that limit, the third thing, that limit must also equal what the function was at that x value. Okay, that was number 3. So the limit is the same as the y value of the function at that x value. So these are the detailed things. Now, I'm going to show you a couple of graphs here of things that are not continuous and talk about why they're not. But again, the simple idea is you should be able to draw the entire graph, or at least the graph on a set interval, between x value of 3 and 7. If you can draw that part of the graph without lifting up your pencil, it's a continuous function. So, looking at this top left graph, you can see there is a hole in the graph at an x value of 3. So, this is discontinuous, is the proper way to say it, but we say there is a discontinuity, I don't know if that's spelled right, at x equals 3. We have that hole in the graph, and remember those three things. You got to meet all three of these things. The first one, for a function to be continuous, the function has to be defined at that x value. F of 3 does not exist. Okay, there's a hole in the graph there, so the function is not defined, so it's not a continuous function. Looking at the top left, I'm getting my left and right switched up. Top right graph, this h of x right up here. It is not continuous because, well, first off, you can see there's a separation right here that happens at an x value of 0, so that's where the discontinuity is. But the reasoning, looking at 1, 2, or 3, the reasoning that this is discontinuous is the limit of this function, this is h of x, at x equals 0, this limit, it doesn't exist. If a function is going to be continuous, the limit's got to exist. This limit does not exist. All right, looking at the bottom left graph, this function g of x, you can see there is a hole in the graph here. It happens at an x value of 4, so the discontinuity will be at x equals 4. But the reasoning is the limit of this function, this is g of x, as x approaches 4, that limit is -2, so the limit exists, but here's the kicker. F of 4, it's not at -2, f of 4 is at 1. So the limit of the function and the value of the function at the x value of 4, they're not the same. That was that third criteria. So we have a hole in the graph there, it's a discontinuity. Looking at this last graph on the bottom right, you can see there's a vertical asymptote at x equals -2. So there's our discontinuity. The reasoning here, well, the limit doesn't exist. Neither the limit doesn't exist as x approaches -2, but the function, you plug in -2, that doesn't exist either. There's a couple of reasons. So at the vertical asymptotes, the function is discontinuous. All right, so not every problem is just going to be, hey, look at this graph, show me where the discontinuities are. So you got to be able to look at the function. And so now, what you're looking for. Vertical asymptotes. Okay, we talked about that before. That's where the denominator is equal to 0 and denominator only. The other thing, and I've mentioned this kind of in passing a few times, is a hole in the graph. Okay, it is called a removable discontinuity. What you're looking for in the equation is a common 0, top and bottom. of that rational function. So a vertical asymptote is when it's a 0 of only the denominator. You have a hole in the graph when it is a 0 on the top and on the bottom of the fraction. All right? Now, the third type of discontinuity, there's a thing called a piecewise function. Basically, it's a function made up of different equations. So you're going to use this equation for these x values, a different equation for these x values, maybe a third equation for other x values. And I'll show you an example of that in a minute. But I want to look at this function here on the bottom of the screen. Find any discontinuities. So we're looking for vertical asymptotes. We're looking for holes in the graph. To find those, factor top and bottom. So this numerator goes to x plus 2 times x plus 3. The denominator, x plus 3, x minus 4. Okay, so we can see that we have zeros of the denominator of negative 3 and positive 4. But we have a common 0, top and bottom. This is the hole in the graph. There's a hole at the 0 of negative 3. Because that is a common 0, top and bottom, that's our hole in the graph. X equals 4, that's a 0 of the denominator only, so that's a vertical asymptote at x equals 4. There is our two discontinuities for this function. Hole in the graph is the common zeros, top and bottom. Vertical asymptotes is the 0 in the denominator only. That's what you're looking for. A piecewise function is the third place to look for your discontinuities. This is a piecewise function. Okay? It is one function, it's f of x, but it's made up of different parts. And so which equation do you use? That's what you're looking at here, here, and here. For certain x values, you use those equations. So now, to graph one of these things, you are looking at, start here. For any x value less than 1, you are graphing x plus 1. All right, so we're going to start at an x value of 1. Basically, just plug in 1. So when x is 1, this x plus 1, so 1 plus 1, that's 2. But notice there's no or equal to. It's x less than 1. So we're going to go to x value of 1. When you plug in 1, you get a y value of 2. We are not including that value because it's not an or equal to. So that's where this line starts. And if we're using all the x values less than 1, okay, this is a line. It has a y-intercept of 1 and a slope of 1. So for all the x values less than 1, y-intercept was at 1, slope of 1. And this just keeps on going. Now, change colors. Now we're looking at the middle equation. For the x values between 1 and 3, we're using this quadratic function. So, plug in the two ends. When x is 1, we got 1 minus 3 plus 4. So that's 5, that's going to be 2. So when x is 1, we're at a y value of 2. Now there is an or equal to there. So basically what we're doing is filling in that hole now. When x is 3, we got 9 minus 9 plus 4. So we go to an x value of 3, our y value is at 4. This is a parabola. It is opening upwards. So I'm going to do my best to make a parabola connecting those points. We could find the vertex, and actually we probably should. The vertex of this equation, negative b over 2a. So the vertex is at 1.5, and a y value of, let's see, 9/4 minus 9/2 plus 4. So we are looking at negative 9 plus 16, was that 7/4? All right, so not a great line, or not great parabola, but somewhere there. Okay, so that's that part of the graph. Now we got the third equation. I'm going to change colors again so it stands out a little bit. For all these x values greater than 3, we're graphing this function, 5 minus x. So the intercept is at 5. Or actually, when we plug in 3, let's be consistent. When we plug in 3, we got 5 minus 3. That's at a y value of 2. Notice how there is no or equal to. So open circle. At an x value of 3, we go to a y value of 2. Now the slope of this line is a -1. This is a piecewise function. Okay, it's a little bit tedious to draw. I mean, kind of fumbled our way through this, but this is what you're doing. For each of these intervals here, you're graphing that function. And so then you kind of just piece them together. So now looking at this graph, on the red graph, it was this red line. It was an open circle here, but the parabola filled it in. So this is continuous. Even though it's not a smooth curve or anything, that doesn't matter. It's defined, the limit exists, the limit's the same as the value of y. We have a discontinuity right there at an x value of 3. That is our only discontinuity because we have to lift up our pencil to graph this thing. And the other thing is the limit doesn't exist because we're approaching 2 and we're approaching 4 from different ends. So that's the idea of removable discontinuities, defining where functions are continuous or where they're not continuous. That is all. Have a great night.